All right, let's see. Talk about today's homework. So you were investigating the double slit by using an approximate technique, which was to consider that the waves coming through two slits are like two point sources here. And each one emits a wave which goes like, in strength, goes like exponential over distance. And then already I told you to simplify that a little bit by not worrying so much about the denominator here. So you're just looking at the total wave function, which is the superposition of these two pieces. Let's take a look at the interference between these two terms. And so we have in the screen over here some distance L. And I think I said point sources are at some distance plus and minus x naught, the x direction. And so if you consider the contribution from these two pieces, if the waves are in sync with each other, then that will be a maximum. If the waves are out of phase with each other, it produces a node on the screen. So what's important here is the relative phase of these two pieces with respect to each other. So we square this to get a probability, a function of distance along the screen. Multiply this by its complex conjugate. And then immediately you see there's two terms. This one times its complex conjugate gives one. This one times it is another one. And then there's we get this term, which talks about the path difference, the difference in the path lengths between these two, and its complex conjugate. This delta R is a function of x, it's a function of where you are on here. It's the difference in the path length between the two. And we're going to multiply by k. The wave number, remember, is the 2 pi over the wavelength. So you're comparing this difference, this delta R, to a wavelength. If this is a multiple of an even multiple of pi, so it's 0 or 2 pi or 4 pi, so if this is equal to an even multiple of, even multiple of pi, or an odd multiple of pi. In this case, you'll get, they will add, so you get a constructive interference, and in this case, you get destructive interference. And so you're guided through approximations to get this difference as a function of x. But that's the basic idea, is that as you move up along the screen here, these distances start off at x equals 0, R1 and R2 are the same. So you're going to get a maximum at the origin. As you go up here, then R1 is increasing, but R2 is increasing faster. And so the difference now will get to be a half a wavelength between the two, and there will be a node. So you get a maximum here, and then a node on either side, and then another maximum, followed by nodes. So you get an interference pattern that goes up from this. Do you have any questions about this? Yeah.
How do you get a even? The fraction's not even nor odd. So how do you
even multiple? What does this mean? Even multiple of pi. Or odd multiple of pi would be minus 3 pi, minus pi, plus pi, 3 pi. So if these are out of phase with each other, so this adds up to be 2 times the cosine, right? So the probability of x2 1 plus the cosine of delta r. If k K delta R is one of these is an even multiple of 2 pi, then the cosine is 1, and this is a max. If these are, if this difference K delta pi is odd multiple of pi, then this will be -1, and you get a node. Okay. So that for the case of the electron, then the guiding wave is coming through both slits, and the phase of the guiding wave is determined here, is given by this kind of amplitude, probability amplitude, and shows why the electrons then are steered away from the nodes and towards the max probability. Okay. Make sense? Okay, so remember earlier we talked about a Gaussian probability density, which is a particular probability density. There are lots of them, of course. And they look at this probability density. Okay, where X has dimensionality of length, right? It's for example, location. What is the probability that an electron will show up in the ensemble at some location X? So for this to be dimensionally consistent, X bar parameter also has to be length. Sigma also a parameter has to be length. See why those have to be. This has to be dimensionless inside the X dimension. And also the probability density itself has dimensionless inverse length. Because you multiply it and integrate it over X. So you multiply by the bin size and integrate. The area under the curve has to be 1. And so you had a homework where you checked that this gives 1. You have to look this up in the table of integrals, perhaps. And also the average of X for this particular function comes out to be like this. Turns out to be X bar. So the Gaussian, if you plot this, symmetrical about X bar. X bar. But X bar might not be at 0. So 0 is over here, suppose. Gaussian is symmetrical around X bar. Integrate it, find the average of X squared. This is sigma squared plus X bar squared. So the uncertainty, statistical uncertainty for the ensemble, given by this, is equal to that parameter sigma. This is a very special distribution, and it's seen commonly in things like a random walk, for example. If you have a coin toss problem, if you have lots of coin tosses, determine how far you walk, then it will, the binomial distribution will converge into the Gaussian distribution. You have a lot of coin tosses. Okay. Now, we're going to go back and study a particular solution to the time-dependent Schrodinger equation. Are there questions about this? Let me just confirm. Does everybody understand how, in general, go from, we had the idea that we have an ensemble, you send out, prepare a system to 1 million people, and everybody report back your value of X, which is measure where the particle is, for example. Everybody reports that back. So you have a list. You have n samples, you have a list. X1, X2, X3. Yeah. And the average, of course, everybody gets to this point, add up all of the samples and divide by the number of samples. That gives you the average value. Okay. You see how to go from this discrete, from having n samples to having an infinite number of samples. You have some probability distribution. You go from this discrete case here to this interval. So I'll do it one more time. I want you to be sure you understand this. Okay, so let's suppose the easy way to see this, we just add up all these numbers, divide by n, but we could sort them instead. Let's put them into bins. So let's. Okay, so we see how many of these values are in each of these bins. So let's suppose we make 6 bins. Let's suppose we have 6 possible outcomes to make it easy to deal with. And we want to find how many ones there are. So in this case, there are 2 ones. So there's some number among this that are in that first bin. And then we look on here and we see how many are in the second bin. So all the 2s come in here, they all have the same value. And we count how many 3s there are. Okay. So then, instead of adding all the numbers and dividing, we would change that sum into a sum over bins. How many is in each bin, and the value of x for that bin. That makes sense? Just grouping them. So I just multiply 1 by the number in the first bin, and I add that to 2 times the number in the second bin, 3 times the number in the third bin. Rewrite it this way. Okay, and this ratio of the number in the bin divided by the total number, that's the probability, it's the fraction of the ensemble that is in each bin. Okay, and now we just take the limit as the bin size is made smaller. We come back here and we say these bins are kind of big, so we want to divide them up to a finer scale so we can get a more precise average. So then that we take that limit as the bin size goes to 0, and that gives us this expression. Okay. All right. So that's it, for example, in Gaussian, it's a special probability distribution. It's a particular example of what I just did. So that's the result in Gaussian. Okay, so let's consider a time-dependent Schrodinger equation. Go back to the time-dependent Schrodinger equation for a free particle. Like warning. Okay, so remind me what let's write down the Schrodinger, time-dependent Schrodinger equation for a free particle. Go ahead.
Should be I H bar D or for respect to
Capital. Psi, which is dependent on both x and t.
And that'll equal negative H bar squared over 2m times partial.
Be able to do this. If I ask for the time-dependent Schrodinger equation for free particle, you should be able to write this. Okay. So we've had different solutions to this. We looked at one solution, which was a plane wave. It's a particular solution. It is one kind of solution. There are lots of solutions to this equation. We had one particular solution. How did we get to it? Well, we said we're looking for a pure mode. So you substitute this into here, and you get the time independent Schrodinger equation. energy is proportional to the frequency. And then we reminded, I pointed out, this is back to the simple harmonic oscillator solution, simple harmonic oscillator equation. In terms of complex variables, it's easy to write the solution to this, either the I kx or either minus I kx. Where k has to be related to the energy, like this. Okay. And then so we can construct the pure mode solutions to the free particle Schrodinger equation for like this, either the I kx minus omega t and either the minus, let's see, right this way, I minus kx minus omega t. These are two solutions, one traveling to the right, one traveling to the left. And we have to have this relationship between omega and k. They have to satisfy the dispersion relation for the free particle. Okay. So that's one possible solution. There are lots of solutions. You're going to investigate another now, and it's a wave function that gives rise to a Gaussian probability distribution. So this is not itself a solution to this problem. There's no time dependence in here. But we're going to find a wave function that gives a Gaussian probability distribution, which is commonly used in quantum mechanics in various circumstances. So we're going to have what's called a Gaussian wave function. So it's a Gaussian-like solution to the time-dependent Schrodinger equation, and it corresponds to a free particle. You're going to look at that. That's written down on page 60, equation 240. I remind myself here. It's a little work to write it down. So this is a solution, and notice that it's a little different. It is a Gaussian, but it's complex. Right? Wave functions in general are going to be complex. And the time dependence is buried inside of this parameter sigma. Yes.
What's that symbol like in the root, like under IT?
Tau. It's Greek letter tau with a subscript 0. See the significance of it here in just a second. It's a time scale. It has dimensions of time. Okay, so let's study this dimensionally. This thing has to be dimensionless again. And of course, x is a length. So sigma here, as a function of time, must be a length. Okay, and sigma naught is also has to be a length. So sigma naught is a parameter in this solution, which is a length, and you'll see the significance of it here in just a second. There's also, for this to be dimensionally proper, this is a length, this is a length. What's inside the square root must be dimensionless. So that's a time, t is a time. And so that parameter tau naught must also be a time. So looking at this combination of constants, there's a mass, there's a length squared, and then there's an h bar. This has dimensions of time. you out here. H bar must have, let's see, dimensions of an energy times time. As if I multiply by omega, omega is inverse time. Frequency. This must be an energy. Okay, so H bar has dimensions of energy times time. Put that in here, you'll see that that ratio of constants must also have dimensions of time. So it's the time scale. Okay, so now I'm not asking you to do this, but it would be a good extra credit assignment for you to plug this into here and confirm that it is a solution. Okay, so you have the derivatives with respect to x, that's not too bad. The derivatives with respect to time, there's time coming in two places. In this numerator here and also here. So it's a little bit of algebra and calculus with algebra to confirm that this is in fact a solution to the time-dependent Schrodinger equation. Okay. But it's a complex function. Now let's check it. Let's see what this looks like at time 0. We can think of the time-dependent Schrodinger equation as telling us how a wave function will evolve. So we start off with a wave function at some time, and then we could solve the time-dependent Schrodinger equation to get the wave function at a later time. So this is an example of that. So let's see what the initial wave function this corresponds to. Let's set t to 0. Okay, so where t is equal to 0, sigma of 0, we set t to 0. It's just sigma naught. So sigma at time 0 is just sigma 0. That's why we call it sigma 0. It's the initial sigma. Okay, so this is sigma 0. And so we wind up with square root of sigma 0 here. I have a square root of sigma 0 over sigma 0. So it's 1 over square root of sigma 0. We have an exponential. Okay. Now it's real. So this wave function at time equals to 0 is real. All the complex part has gone away. And if we square this probability at t equals to 0, it's a real function. So we just multiply it by itself. So we get this 1 over 2 pi to the 1/4 becomes a 1 over square root of 2 pi. And square root of sigma naught squared becomes sigma naught. This multiplied by itself is a factor of 2. Okay. Now, what does that look like? Yeah, like Gaussian. That's the Gaussian centered at 0. When x bar is 0. So this solution initially corresponds to a Gaussian probability distribution. But it's going to change in time. That is, the Schrodinger equation is going to evolve. Is this a pure mode? No, not a pure mode. It doesn't have the simple form of a function of x times e to the minus I omega t. There's no single frequency in this thing. It's a mixture. It's a superposition of pure modes. Look at it now. It is a solution. And it corresponds to a Gaussian probability at time 0. Okay, your homework is to figure out the probability distribution at other times. So can I erase this? Okay, no? I finished. So let me point out here, by the way, we notice this is the sigma standard deviation for the Gaussian probability distribution. Sorry, I'm looking at equals 0. Sorry. At equals to 0. It's the width of the Gaussian probability distribution. That's what sigma naught is. At equals to 0. And in time, this is going to change. This complex function is going to have a different probability. So note that sigma naught is the initial width of the probability distribution. And this time parameter, tau naught, depends on that width. So the narrower the distribution is initially, shorter this time is. The longer, the wider the distribution, the longer this time is. So we're going to think of this as confining the particle in some region with the probability distribution, and then see how long it takes to evolve. So, and exactly what I mean by evolve here, we're going to solve here. Your homework problem is to take this wave function and calculate the probability distribution for any time. Multiply the wave function by its complex conjugate. When you take the complex conjugate, you got to find everywhere there's a complex number, you change it to its complex conjugate. Okay, so here's the wave function. Everything is real here except for sigma. Sigma of t. So what is sigma of t is this? What is this complex conjugate? This complex number. What is this complex conjugate?
Square root of 1 minus I t over t.
Now, taking a conjugate is easy. Everywhere there's a t, an I, you flip it. Flip the sign. Okay, so what is sigma star times sigma? Multiply this number by its complex conjugate. Multiply these together.
4.
No. Not 1. So in fact, you take the square root and you take the things that are under the square root inside the square, you're going to multiply that by its complex conjugate. It's rough.
Would it not be, forgot to put the sigma naught, beginning of the sigma?
Oh, excuse me. Yes, thank you. Sigma naught here. And sigma naught here. But sigma naught is a real parameter. It's the initial width of the probability distribution. So
It goes like a constant.
this would be sigma naught squared here. What goes like a constant?
So it goes like a constant.
Sigma naught is a constant.
Okay.
It's the initial width. The width is going to be changing in time, but this is the initial probability distribution. It started off having that width. Okay, so just in case that went by fast, this would be an good extra credit for you to substitute this into the time-dependent Schrodinger equation and confirm that it's a solution to the to that equation. Okay. Anyway, we're multiplying sigma star by sigma by its complex conjugate, which that's going to happen here. When we multiply this by its complex conjugate, you're going to have 1 over sigma star. Multiply those together, you get a 1 over sigma star times sigma. This is going to occur right here, and then it's going to be another thing you've got to figure out over here. But this is going to be one thing you have to figure out. So what is this? It's just multiply it by its complex conjugate. Multiply it out.
Was
Yes, sir.
t squared over tau squared, tau naught squared.
Yep. Okay. So when you take, let's write down psi star here. Psi star only thing that's not real in this expression is sigma of t. So we have a complex conjugate here. Okay, so when we multiply these two, the pre-exponential part, we're going to get in the denominator, we're going to get this. Okay. All right, so that's one place where it occurs, but here's the other place. I'm going to get you partway started here. More complicated, but it's not bad. Right. Okay, so before you start the homework, you might want to review this video here. Okay. Or maybe you feel like this is enough. Okay, so we're going to multiply these two exponentials together. Multiply two exponentials. What does that give? Say again?
Add.
You add the exponent. So you've got minus x squared over 4 sigma squared minus x squared over 4 sigma star squared. Here's sigma. I erased the sigma star. So in fact, there's a common factor of x squared over 4, so you can a negative sign. Pull that out. This is 1 over sigma squared plus 1 over. Okay, so sigma is this. So it's 1 over and it's squared. Sigma naught squared. 1 plus I t over tau. I want to add to that its complex conjugate. Just put the sign. If you're a little worried about, puzzled about how to handle complex numbers in the denominator, it's like rationalizing. It's fraction. 1 over x plus y, 1 over x plus iy. Let's write this in the standard Cartesian form. This is not in the standard Cartesian form because it should be a real part plus an imaginary part. This is 1 over something. How do we convert this into a standard Cartesian form?
Multiply by the complex conjugate.
Multiply it by its complex conjugate. See? So what do we get in the numerator now? We have x minus iy. What do we get in the denominator? Complex number multiplied by its complex conjugate.
Square root of x squared plus y.
It's actually x squared plus y squared.
Oh,
Yeah. Right. The absolute value is square root of x squared plus y squared, but complex number times its complex conjugate is the length. The square is the square of the length. Right? This works out to be x squared plus y. Right? Know how to do that? Okay. Just multiply this out. Got two second order polynomials, or two polynomials with 2 terms. You multiply it out, you get 4 terms. 2 of them cancel out, and you're left with just 2 terms. So you're going to do that with this. Okay. All right. So you're going to show, when all is said and done, that this is a Gaussian. It's still a Gaussian, but it's a little different here. So the probability is written down in here. Okay, you'll get this answer. We're going to this new symbol here, sigma for the probability distribution, looks like sigma naught squared over tau squared. So you're going to confirm that. You multiply these wave functions out, you're going to get something that looks like this. So now this is a Gaussian. Again, it is a Gaussian, but the width is dependent on time. So that means that we start the wave function out as like a Gaussian, and it corresponds to a Gaussian probability. Now, over time, it's going to evolve. It's still a Gaussian, but its width has increased. Time is gaining. This width will increase, so the probability now is Gaussian with a wider distribution. Sigma corresponds to the width of the distribution. So it starts off with width sigma naught, and after some time t, it's increased to this width. And the time scale for that to occur is given by this parameter tau naught, by the initial width. So if we start something off really narrow, it's going to spread faster. If we start something off already pretty fast, it's going to spread, but not as fast. So where are we? What does all that mean? Remember, this is a solution to the time-dependent Schrodinger equation. When we did the particle in a box, we could find the particle to some box. And the Gaussian is kind of like that. It's confining it to some region, at least the probability, to some region sigma. It's within, most of the ensemble is within 2 sigma of the average of 0. Now we wait for some time. This Gaussian is spreading. What does that remind you of? Gaussian that's spreading. Yeah.
You're talking about like a wine cork flowing in water that's spreading out.
Yeah. A drop of dye in the water will spread out, and the concentration of the dye will be a Gaussian. Will approximately a Gaussian. And the width will increase in time. Notice here, if we wait a long time, that is, if t is much greater than t naught, we can replace this 1 plus t squared over t naught squared. We can replace that by t over t naught squared, the t squared over t naught squared, right? For a long time, for t much greater than t tau naught, this goes like sigma naught t. The width is increasing linearly in time. This is over tau naught. If this is much larger than this, the 1 is negative. It's a huge number. So I can neglect the 1, take the square root of t squared over tau naught. Sorry about that. Okay, so this is telling us something about the nature of the Schrodinger equation and particles that are governed by the guiding wave. You localize a particle, like put it into a Gaussian, and the Schrodinger equation tells you that the guiding wave is going to start pushing the ensemble out. It's going to start diffusing out, similar to a kind of diffusive process. So there's some similarity between the Schrodinger equation and a diffusive process. That means there's a stochastic part that's coming back to the stochastic part of the guiding wave structure, which is knocking the particle around. For a free particle, there's no resonant structure. So it's the stochastic part is largely guiding what's going on. And so you get, it's like a random walk, pushing the particles. So the ensemble is just being gradually pushed out. Yes.
Wouldn't that go against the law of entropy because it's kind of evening out, or is that an opposite way of thinking?
So I guess I need to ask what you mean by the law of entropy.
But like everything will like go to like non-organized, or everything moves away from like
Well, okay, so this, I mean, spreading out, right? That's what the die is doing. In the example of the die is spreading out. That's not violating the law of entropy, which is with
more chaos.
but entropy is poorly understood. If you remember, when we briefly studied thermodynamics, the law of entropy it was expressed in terms of taking heat from one place to another and have a requisite amount of work done. That's a easy thing to understand. The entropy is one of those areas that needs to be worked on. You need to have a PFR thermodynamics to help us understand what entropy is. It's poorly understood. Some of those things that needs to be digested.
I'm going off like the chemistry, like,
Yeah, I know.
yeah.
But I mean, this makes sense in terms of kind of diffusive behavior, just kind of spreads out, right? And that doesn't violate any sense of any thermodynamic law. Yes.
So this is, if you, this is still talking about like the ensemble of these particles, right?
Right.
So if you have the ensemble is spreading out within time.
Yeah.
So what would that,
So let's remind ourselves about the ensemble. How do we do this? So I'm going to prepare an ensemble corresponding to a Gaussian probability distribution. That means if I hand it out and I tell you, everybody make your measurement right away. Don't wait any time. Everybody reports back their probability, the values, we make a histogram, it's going to look like this Gaussian. Now I say, I'm going to do it again, but I want you to wait 10 minutes before you make your measurement. And we're going to find out that the probability distribution is still Gaussian, but it has expanded. And whether 10 minutes is a short time or a long time depends on this parameter. Depends on the Planck's constant, it depends on the mass of the particle, and it depends on the initial spread. How tightly we confine the ensemble to begin with. Okay, so let's look at that. A particle with low mass is going to have a short time. The lighter the mass, the less the mass, the quicker this expansion is going to take place. Also, it depends on the initial confinement. Something that's confined to a narrow region, a small value sigma naught, is also going to take less time to expand. So you're going to calculate this constant for a car in a garage. How long does it take a car in a garage? What is this time scale? It's going to be long. Then you're going to calculate this for an electron in a hydrogen atom. So the mass of the electron here, this would be on the order of an angstrom, half an angstrom, something like that, the size of the hydrogen. You'll find the time scale is much quicker. So of course, the important parameter in all of this is Planck's constant, really small.
so this is not particle in the box, though, right?
No, it's not. So how do I confine this ensemble? Well, that's a practical question about how do you make an ensemble like this. But this just in principle, if I could make such an ensemble by confining it, then I would get this result. Right? I could have done a particle in a box, but remember this is a free particle, so how would I have done it? I would start the system off with a wave function for the particle in the box, but I have to take walls away. I have to let the particle out. So that would correspond, I could do a similar thing, maybe it's easier to imagine doing that. Let's put it in the ground state. The wave function, remember, for the particle in the box. The ground state is this. Okay. And 0 outside. Okay, now, so let's start it off like this and take the walls away. So the wave function immediately afterwards is going to look exactly the same, except there's nothing holding it in anymore. So it's going to start expanding. So we could solve this problem. And this will have a solution which is somewhat similar to this one. There's going to be a time scale for the expansion of this wave function. This thing is going to expand outward from where it started, confining it into a box. And there's going to be a time scale which is very much like this. So this time scale doesn't depend actually on the details of the wave function. That is, something like this will also expand, and the time scale will be something like this again, where sigma naught now would be L, the size of the region you've confined it to. So there's going to be a time scale for the expansion of this wave function, which will look like this, where L is now the size of the region you've confined it to. This is mathematically harder to work. And so we're not doing that one, but then this one is easier to see about how you would set it up. Put it into a box and box it, and then let it expand out. This one is how do you get it into a Gaussian begin? Okay, so just imagine that there is some means by which you could do that. The reason I'm doing this one is because it's mathematically more practical than this problem. But the principle is going to be the same. And in fact, we get a nice simple analytical solution with a time scale here, so that makes it simple. This one would be a little harder to solve. There's going to be something like a time scale, which is going to be probably a mixture of time scales. So there's going to be a spectrum of time scales, but they're all going to be something like this. And so there's still a time scale for the expansion away from the initial confined state. So physically, however you confine the electron, then you take the confinement away and let it expand. And the Schrodinger equation tells us how the guiding wave is jittering the particle around. So it's doing a kind of random walk. Wave function, the probability is expanding. Yeah.
That view is one, that'd be the measurement of just one particle, right? Like, there's only one particle in the box, right?
Yeah.
We're linear with the.
We're only doing one particle at a time, but we have an ensemble
Exactly, yeah.
of these, right? So, and you always have to think of this as in terms of an ensemble, not in terms of a single particle in a state. Making a million copies, everybody make a measurement, we get a probability distribution corresponds to an ensemble, not to a single particle. We say an ensemble of single particles, right? It's a more complicated problem to put two particles in a box. I'm not going to get to that until later in the course. How do you deal with multiple electrons in an atom, for example? Lots of atoms have more than one electron. So how do we deal with that? We're not working on that yet. It's coming later. Just got to get our feet wet onto even just the case of one electron. Any questions?
What? Is it stupid to ask why it spreads out? Or
I gave you why it spreads out. Why does it spread out?
is it not confined anymore?
No,
Is something trapping inside there? Go away.
no. Why does it spread out?
Stochastic part of the weight.
That's the stochastic part of the guiding wave structure. It's knocking the particle around, it's jittering it. So the ensemble is going to start to spread, right? Some are going to the left, some are going to the right, it's doing a random walk. So the distribution is going to spread in time. Yes.
I'm trying to tie it back to the impetus idea.
Yeah.
The guiding wave is the impetus, is the reason that particles have impetus, right?
So the guiding, there are various things that can give a force to a particle. The guiding wave is one of those. But you have a box, so you somehow you have something that can confine the particle that's producing the force that's keeping it in there. But all this we did today was for free particles, so there's no other force at work. It's just the guiding for this. So now we can, we also considered the particle in the box, and we said, why can't it go below the 0 point? And that's, again, there's a guiding wave that keeps knocking it around. So now let's take the box out, the walls away. That stochastic force is going to start spreading this distribution out. This this is all implicit in the Schrodinger equation. We don't have the details of the guiding wave structure and the interaction with the particle. Schrodinger equation doesn't have all those details. It's got the net effect on the ensemble after some time. Okay. See you on Wednesday.